This video contains examples of coordinate systems. Check the solutions to the problems here in Dynamics of Rigid Bodies. The first example states, in the design of highway curves, the standard acceleration for cars traveling at a speed of 25 meters per second should not exceed 3 meters per square second. With what radius of curvature does this standard apply? What if the speed limit is raised to 30 meters per second? What radius of curvature should be applied? The problem requires radius of curvature, which we can find in the normal tangential coordinate system. From the premise, the formula for acceleration is the root of the squares of tangential and normal accelerations. The problem gives acceleration as 3 meters per second squared and velocity as 25 meters per second. This magnitude of velocity can be used to differentiate the tangential acceleration, which is the derivative of 25, and that is equal to 0. With the tangential acceleration as 0, we can equate the acceleration as the normal acceleration, which we can further notate as the square of velocity all over the radius of curvature. If velocity is given as 25 meters per second, we can say 3 is equal to the square of 25 all over ρ, where ρ is taken as 208.33 meters. The next question is to check the change of radius if the speed is raised to 30 meters per second. Using the same equation, plug in 30 for velocity to have 3 is equal to the square of 30 all over ρ. ρ is then taken as 300 meters. The next example has a particle moving along a path described as x squared plus y squared is equal to r squared. It further states that the y component of the velocity is 2r cosine of 2t. The task is to identify the x and y components of its acceleration. From the given path equation, x squared is taken as the difference of the squares of r and y. Also from the next given equation of the y component of velocity, which is 2r times cosine 2t, integrate it to have y equal to 2r times sine of 2t all over 2. Simplify this further by taking out 2 to have r sine of 2t. This expression for y is then plugged into the first equation, so we get x squared is equal to r squared minus the square of r sine of 2t. Expand the square and factor out the square of r from both terms to get x squared is equal to r squared times the binomial of 1 minus the square of sine 2t. Now take a look at the binomial where we can use basic trigonometric identities. Particularly the squares of sine and cosine of an angle is 1. Group 1 and sine squared together to copy the 1 from the equation, so we can have it shortened as x squared is equal to r squared times cosine squared of 2t. Now we can take x as r cosine of 2t. Let's differentiate this to have the x component of velocity, which is the constant r, times the derivative of cosine 2t as negative sine of 2t, times 2, so v sub x is negative 2r sine of 2t. By differentiating v sub x further, we get the x component of acceleration, and that is negative 2r times the derivative of sine 2t, which is cosine of 2t times 2, making a sub x as negative 4r cosine of 2t. The y component can be taken simply from v sub y of 2r cosine of 2t. If we differentiate it once to get a sub y, that would be the constant 2r times the derivative of cosine 2t as negative sine of 2t times 2, which can be shortened as negative 4r times sine of 2t. Example 3 has a particle moving along a circular path of 300 mm radius. If its angular velocity is theta dot equal to 3t squared in radians per second, where t is in seconds, determine the magnitudes of the particle's velocity and acceleration when theta is equal to 45 degrees. The particle starts from rest when theta is 0 degrees. With the two parameters already provided, we can determine the others. From r, which is 300 millimeters, or 0.3 meters, r dot is then 0, and also r double dot as 0. The angular velocity theta dot is also given as 3t squared, and by integrating this parameter, we get theta. The integration results to 3 times t cubed all over 3, which is then simplified as t cubed. Another thing to take note from the premise is this statement stating that the required velocity and acceleration should be when theta is 45 degrees from 0. Learning that theta is t cubed, we can compute for time by placing 45 degrees as theta. But then, it has to be converted into radians. T is then computed as 0.9226. Having this parameter determined, theta can then be computed by plugging t as 0.9226, that is, theta as 0.9226 cubed, giving theta as 0.7853. Next is to identify theta double dot, and that is determined by differentiating the equation once again. We get theta double dot as the constant 3 times the derivative of t squared, which is 2t, simplified as 6t. Again, plug time as 0.9226 to have theta double dot as 5.5356. Last value to determine is from theta dot, which is simply 3 times the square of t, which is 0.9226, giving theta dot as 2.5536. After identifying all the parameters, plug the relevant ones to the equation. Start with the velocity with the equation the root of the square of r dot plus the square of r times theta dot. R dot is 0, r is 300 millimeters, and theta dot is 2.5536, giving velocity as 0.766 meters per second. Next is acceleration with the formula of root of the squares of the radial and transverse components. After plugging the values, we get the root of the squares of 1.9563 and 1.6607 to give acceleration as 2.566 meters per square second. The fourth example is about kinetics of particles, particularly Newton's second law. The problem states, if motor M exerts a force of F is equal to 10t squared plus 100, that would be newtons, on the cable, where t is in seconds, determine the velocity of the 30 kg crate when t is equal to 4 seconds. The coefficient of friction between the crate and the plane is mu equal to 0.25, and the crate is initially at rest. We use net force equated as m times a to solve the problem. The net force comprises of all types of forces involved, which would be the applied force and friction. The normal force is computed as m times g. That would be the mass of 30 kilograms times gravitational acceleration of 9.81 to give 294.3 newtons. It is necessary to determine normal force to solve for friction, which is the coefficient times normal force, that is 0.25 times 294.3, which is 73.575 newtons. Plug this into the equation to have 10t squared plus 100 minus 73.575 is equal to 30a. This can be shortened as 10t squared plus 26.425 is equal to 30a. Rearrange the terms to isolate a, then integrate it to have velocity, with the formula 1/9 of t cubed plus 0.88t. By placing t as 4 seconds, velocity is then computed as 10.63 meters per second. With a similar example, check the change if the crate is heavier at 35 kilograms and the coefficient of friction is reduced to 0.2. The change in mass also changes the normal force as 35 times 9.81, which results to 343.35 newtons. Then friction is computed as 0.2 of the normal force, which is 68.67 newtons. The force equation is 10t squared plus 100 minus 68.67 is equal to 35a. Reduced to 10t squared plus 31.33 is equal to 35a. Isolate a and then integrate the whole thing to have 2 of 21 of t cubed plus 0.9t, and at t equal to 4 seconds, acceleration comes out as 9.68 meters per second.